Hello and welcome to another C++ tutorial. So this time around we are going to be taking a look at the concept of operators, and in particular looking at operator overloading. So how we could take something like our own custom class and we might add in support for the plus operator or for the divide operator, things like that. So we're going to take a look at how that works, some of the catches and limitations with that, and then we're going to see what we can create. So let's dive on in. So this is already in the repo. What I've already done is, what I do in other projects is I set up my example of how I want to be able to actually use this first. So for this one, I wanted to be setting up a vector class, and in particular, in this case, a 2D vector. Because it's a really handy one for demonstrating the different mathematical operators and some of the kind of considerations there with that. So what I've written is I've written the code to actually make use of this vector class. I haven't actually created the vector class yet though. But I've got my example of exactly how I want it to work. And this is something where one of the ways we can approach development is something called test-driven development. So we could actually write unit tests, which are small, typically little snippets of code, that what they do is they validate what we have actually written. So they test all of the aspects of the functionality of it and make sure that it gives the correct outputs based upon the inputs that have been provided to it. So this can be really handy, in particular for math libraries. It's a really good way of validating that the calculations are correct. And then there's further stuff you can do, like integrating this into your release processes, your day-to-day development processes, to make sure stuff doesn't get broken. So it can be a really handy approach. But sort of the very, 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 very much cut down version of that I do is just implementing the code that's going to use the stuff before implementing the actual backing code for it. Just make sure that I implement what I'm setting out to. So to begin with, I'm going to create our vector2 class. Now, I'm creating this as a dedicated one where the x and y coordinates are stored in floats. There are, if you're looking at math libraries, it's quite common to see templated versions of these where they can work with integers or floats or doubles, things like that. I'm going for one that's specifically just floats, and the reason for that is because I want to focus on showing the operator overloading rather than diving into sort of the template aspect and things like that. So first thing I'm going to do is I'm going to add my class, which I'm going to call vector2. So I'm splitting this up into the separate file just because that forces us to have to deal with a few extra considerations that we otherwise wouldn't. So, okay, that's good. Let's start to get some of the basics going here. So I'm going to start uncommenting lines. And we'll include our header file here. Because it's one that's within the project, we use the quotation marks. So, okay, and I'll uncomment this one also. So we've got a few different things that are currently failing, and that's because, okay, we haven't set up a constructor that can take in floats yet. We haven't defined this one member there, and we haven't defined the x and y, anything like that. So there's a lot of bits we haven't defined. So let's start creating those. So good practice in C++ is generally breaking up our header, the declarations there based upon variables, and I'll usually group public and protected and private separately, grouping the functions separately as well. I think just keeps things neater and cleaner. So we'll have our float x and our float y. And we can go, and I've made those public because it's really handy with a vector to class to be able to directly access them. Now, depending on what type of class you're creating, having those be public may not be what you're wanting to do. If you're creating some other type of class that operators are being performed on, you may very specifically not want them to be directly accessible like that. So I'm doing this because this fits the usage pattern that I think is ideal for vectors, but it may not be what you want to be doing for your particular class. So we can see that will make this one happier. And we've got a bunch of ones here that are already happy in terms of with the constructors, ones that just work out of the box. But we can create this constructor that takes in floats. So because it's a separate function, I'm going to put it in its own separate public section. So we know we want to have a vector2 float in x and float in y. Now, because I'm going for having the separate header and CPP file, I'm going to just create the declaration for it there, and I want to create now the implementation, which that's pretty straightforward. We can just handle it like this. So, okay, that makes this one happy. But then this one is grumpy. And the reason it's grumpy is because the only before I had no constructors. So having something where it's not got an explicit constructor being used was fine. So now, because I have this set up, I have to actually have a empty default constructor like that. So we can use refactorings, or we can just directly, so part of this is coming from a plugin that I'm using, but you can often with Visual Studio, you'll see these little fixes, so you can go and create the definition of it. So I'm generally doing that through the add-on that I use, but you can also do that directly. So with this, okay, I can say x, we default initialize these to 0. So, okay, that's good. This is still grumpy, and this is something where I will actually put these here. Again, public. So with vectors, it's often a really handy thing to have a definition for like a vector that is all ones or a vector that's all zeros. So what you'll commonly see is that handled like this. So a static const 1 and a static const vector2 0. Now, how we actually set those up is we're not giving them the value here. What we do typically is we then go over to our CPP file, and then we say const, we give it the type, so vector2, then we give it the actual reference to the particular variable. So that is 1 and 1. And then we have a similar thing with vector2. Whoops. Autocomplete is messing me around at times. So we have 0. And although I could just let it run the default initializer, this is one of those cases where I just, honestly, for my own peace of mind, want to be very explicit with it. So, okay. That's fixed all of these errors, and we can double check by doing a build so we get no errors. So that's good. So let's start to set up some of these other things. So first thing I really want to get working is being able to support this stream output operator, because this is something where it's going to make testing and debugging a lot easier. So this, we might expect with this, because it is an operator, that stream insertion operator is just another operator that exists. You might expect to be setting that up inside our class here. And we actually don't. And if I get here and hash include our IO stream, just so we've actually got it. So I could attempt to set this up in here. So how that would look is, could say something like, so it has to be static because it's returning a stream. So this is one of the things, the way the stream operator looks is it's a OStream reference is what it returns. The operator looks like that. It takes an OStream in, and it also takes on the other side a vector 2 in this case. So we could try and set it up like this. And if we go over to here, you can see that it's actually still grumpy, saying that it can't find it, that the implementation doesn't exist. And that's because when you create something that's static within a class, this is how you refer to it. So this needs to actually sit outside of the class. And there are a couple of operators where this happens with. So what I actually do is I bring this here and I put it outside of it. Because it's outside of it, it doesn't actually need to be static. What I'll find is when I go back here, it's now okay. So this is something where what that actually means, and this is a really good thing, is there could be a time that the stream insertion operator doesn't support. And we can add support for that without needing to go and modify that particular class, that particular type of data. Because it could be something from a third-party library that we might not be able to modify, and we don't need to. We can just create this standalone function that sits outside of it. So again, I'm going to create the implementation of this. So we create that definition. So how this looks, it's kind of up to us. We have a lot of control over what we want this to do. What I would generally do in terms of how I would set this up is we do our output stream, and then we output what we want this to look like. So vector x, comma, and we then have our vec.y, and then we close that out. Actually, we don't want to put a new line, but then we just return that. So I'll actually do the trick. Now, a thing you might wonder is, okay, if we were doing this and we did have these as private, so let's see what happens and how we would work around that. Because as soon as I do that, this is immediately grumpy, which is expected, because from something external, we're trying to access it. However, we have seen before the friend declaration. So you could actually say here that this is a friend of the class. And what we'll find is this now works. So if you have your member variables that it's outputting here are private, then you need to mark that operator as being a friend of it. So I'm going to return that back to public. I'm going to put a comment here, only necessary if x and y are private or protected. Just a handy thing to be aware of with it. So, okay. This means this initial block here probably should actually work. So let's test that out. So you can see we're outputting here the expected results and what it did output, and those line up, which is great. So that's good. We've got a few of our basics here up and running. What if we start setting up some of our things like our math operators here? So these won't actually work by default because we haven't implemented them. So we have to actually set these up. And the way these work is a little bit different depending upon the particular operator. So we can see I've intentionally set up so that we have plus, minus, as well as plus equals and minus equals. So what I'll do, and one of the reasons why I'm sort of separating it out and implementing it like I am, is because if you've come from C#, there are a bunch of additional operators that just sort of are already there and working. Whereas with C++, there are some ones that will be implicitly declared, but not too many of them. They're generally ones focused around construction. So you'll see I won't be implementing things like the assignment operator. I'd only need to do that if I was doing something more complex when an assignment happens. And we're already doing an assignment here. So assignment operators, things like that, already are going to work fine. And just in case it's something where, okay, it only works with the constructor, I could also do D is equal to A, like that. And we can see we're not getting any errors from that. So stuff like assignment operators, there'll be an implicit version that's already there. But there won't be for any of these mathematical operators. So how I would set these up, so firstly, we're going to make plus and minus work. So vector operator plus, and we support vector 2 in other. And we have our subtraction 1. What I will actually do, just because of how I would normally lay these things out, I am actually going to put these below our constructors, just because that's how I would normally split these up. So that's good. And we can again use the setup for implementing those. So we just create that implementation. So a lot of IDEs will make it easy to go and just create the definitions for this. So, okay, well, plus and minus, pretty straightforward in what they need to do. It's already kind of given us a little bit of a helper here. So this would end up being x plus in other dot x, then y plus in other dot y. For subtraction, we would have x minus in other dot x and y minus in other dot y. So we've implemented plus and minus. So the thing we might wonder there is, okay, does that automatically mean plus equals and minus equals works? Because we've kind of defined how to do plus and minus, and plus equal, and we didn't need to specifically define the assignment operator. So is it able to infer that? And the answer is no. It can't actually infer that. So if you want to support plus equals and minus equals, you need to add those in. Those are a separate operator. And not only are they a separate operator, but they actually return a reference. So we're going to implement those. And we can do the same here. The prompt there does not always reliably show up, which is more than a little bit annoying, but you get that. So what we would do here is x plus equals in other.x, y plus equals in other.y. We return a dereference of this. Then we do similar thing down here for minus equals, except we change the operator. So what we should now find is there's not anything it's getting grumpy about error-wise, which is good. So let's run that and make sure we're getting the expected outputs. So we can see that yes, those are coming through correctly. So that's good. We've got some basic manipulation of the vectors happening there. We can do additions, we can do subtractions, we can do it using plus equals, minus equals, which is good. What about if we're having it interact with other types? So things like these scenarios here, where what we're doing is we are scaling a vector. That's a really helpful thing to be able to support. So we can do that. And again, we set up operators, and it follows a very similar process to these. The difference that we get, and I am actually intentionally just going to copy and paste because we can, these, whoops, we have a multiply and a divide, and times and divide equals. This, well, because we're just providing a float, we don't need that to be a const reference. So this is the multiplier. This would be the divisor. So we just have these set up. And being able to scale, a float is or our vector is really handy. And an important thing with operators and setting them up is C++ allows us to override a lot of operators. And I do mean a lot. Like there is a huge number that you can overload. And the temptation there can be to use operators to do things that we would normally use a function for, and to do things that are kind of non-standard. So part of the reason I'm using a vector here is that's a common one where I do see that happen with. So one of the common vector operations, in particular in games that we use a lot, is the dot product. And I've seen, I think, every possible variation of ways of doing that in different vector libraries. I've seen ones that use the pipe symbol. I've seen ones that use a function for it. I've seen ones that use other different operators. And you could set up here all of your things like dot product and cross products and all sorts of operations like of that by setting up different operators. But I kind of recommend against it, especially for things like dot and cross product. And a big part of the reason for it goes back to that thing where I said of every math library I've used tends to do it slightly differently. And so it makes it very confusing because you can have something where the operator does a particular thing, but it's not obvious what it does until you look at the internals of it, which means you need to not just understand how you use the dot product, but you need to understand how it's calculated. So I don't think that's good practice. I think when you're setting up a class, when you're setting up a library, the interfaces should be intuitive. So while we can overload so many of the operators, it's kind of ridiculous, all of the combinations that we can override. I don't recommend doing that except where it makes logical mathematical sense for things where it doesn't, I would just set up a function. So that's why I would implement things like plus and minus with other vectors. Multiply and divide, I would generally only implement that with something like a float, or if I had matrices as something supported, then I would have support for multiplying vectors and matrices would make sense. But I wouldn't generally implement things for multiplying and dividing two vectors, because that's an operation where every library defines it a little bit differently. And I think we should be trying to make stuff consistent, clear, readable. So while you can overload every possible operator pretty much, the list of ones you can't overload is much smaller than the list of ones that you can. Resist that temptation. Keep it logical. Keep it so that it makes sense. So let's get these implemented. So again, we'll just create the definitions for all of these. I do wish it provided just a bulk thing for implementing that, but I've never found the bulk option for just implementing all of the definitions. It does when you're doing things like abstract and that, but not for things like this, unfortunately. So this is pretty straightforward. X times our multiplier and y times our multiplier. Same thing here. We do x divided by our divisor and y divided by the divisor. Times equals or plus equals, again, work out pretty similarly. So we do quite similar process to what we were doing for the other ones, where we do x times equals our in multiplier, y, we scale that, and we return a dereferenced version of this. And then same logic again. And returning that. So we can test that out. We've uncommented these ones, so we can make sure that those actually look correct. So again, all of those values are coming through exactly like we would want them to be. So that's good. And we'll fix up the extra space I have here. So, okay, we've seen how we can implement operators for mathematical manipulation. We've seen how we can set up things for outputting it. What about stuff like comparisons? Because this is something where, in particular, if you're coming from C#, in C#, this would typically already work to an extent. It wouldn't necessarily work the way we want it to, and it wouldn't necessarily work the most efficient way, but it would technically still work in C#. Whereas in C++, it won't. We have to actually set things up for this. So what I would do, and this actually comes back to how we had to declare this one outside, we actually have to do the same for these comparison operators. So how these ones look is they return a bool, and then we have const vector 2. With this, I always go for the convention of making it clear which one is on the left-hand side and which one is on the right-hand side. It does follow the order that you would expect, but I do always just believe in making it kind of explicit with it, because I think it just avoids potential problems. Now again, if we had the data as being private, we would need these as being friends. So what I'm going to do is put them up here with the friend declaration, just so that if you do want to experiment with things like having the x and y as private, and you could have functions that return a reference to it if you want to have them accessible that way. This just gives us a way of demonstrating this, which I think is handy. So we'll create these definitions. And now with this, we are comparing floating point numbers, which there is a level of imprecision to floating point numbers. So what I would typically do in a case like of this, and this is something I would specifically only do with vectors. And I'm going to put another public here. And what I would do is I would actually have a equals function. And I would have vector2 in other. And then I would allow a tolerance to be provided for this. And you could hard code in a particular value here. Usually what I will use is we can actually ask standard numeric limits. Can tell it I want the numeric limits for a float and I want its epsilon value. That epsilon value is the smallest, so if a floating point number is 1, so its value is currently 1, the epsilon is typically the smallest amount that can be increased or decreased by from 1. So it usually provides a pretty good tolerance value. So give that just as a default, and then I create the definition for that. Now, one of the things it doesn't do here, but which the other add-on that I have does, and that I'll actually bring over here, is I am a big fan of the coding style where in the header, you obviously have the default value provided, but then in the implementation of that function, you don't have the default value there again, because that would be redundant, but you have it commented out so you know in that function that there is a default value being given and what that default value is. So having equals, which we'll come to the implementation of that in a moment, the reason for having that is it then simplifies what we do down here. So this would be LHS equals RHS, and this would be the not of that. So the reason for doing it this way is we still have that out-of-the-box support for equality and inequality operators, which I think is good. But if we're wanting to do that comparison with a different tolerance, which we might want to and add for some reason, if we're wanting to do that, then we have the means to do that. And everything for these comparisons routes through a single function, which I think is just generally, it's cleaner. It means if something is going wrong with a comparison, then we know there's a single point to check for it. What this code would then end up looking like is I want to get the absolute value of the difference between in other x and rx. So that needs to be less than or equal to our tolerance value. And we do the exact same thing, but with y. So the reason we're doing this fabs here is the absolute value of a floating point number. So that means that if something is negative, it will make it positive. If it's already positive, it remains as positive. So it just means that we don't need to check, okay, is it less than or equal to the positive value of the tolerance and greater than or equal to the negative value of the tolerance? It just gives us a single check that we're able to do. So it keeps the code cleaner and neater. So, okay, that should mean our equality and inequality operators are working here. So what we should find is, because A and B definitely do not match, so we shouldn't see this, but we should see this. and we should see this. So there's two outputs we should see. So we can see A and B do not match, and we can see that C is matching our vector 1. So that's good. We've got our main operators happening there. So the final thing that I want to set up is our dot product function. As I said, I specifically would not ever set this up as an operator because I don't think it's good practice to do that as an operator, just because it's often confusing and different libraries use different approaches for it. So I think using a function is the best approach. Now there's two ways I could set this up. One is I could set it up as a function that you give it left-hand vector dot right-hand vector. That's a pretty handy interface to have. So that would look like this. Vector 2, and I'll make sure we're applying that as being a const reference in other. And in this case, actually, it doesn't really matter whether it's left or right-hand side, so I would actually stick with it being called in other. Again, mark that function as const. But the other way that I might want to write this is I might want to be able to just go vector 2 dot. So a function that sits on the vector 2 itself. So I'll show you how that would look as well. That would be a static function. And it would be dot. Now, because it's a static function, it belongs to the class, not an instance of the class. So what I would do then is vector 2, and in this case, although with our dot product doesn't actually matter which way we get these around, I would just, for consistency with other code, explicitly indicate left and right hand side. Now this one doesn't need to be marked as a const function because it's not actually running on an instance of the class. So I can create the definitions for these. Get this one. So this one, pretty straightforward. We return x multiplied by inOther.x plus y multiplied by inOther.y. For this one, I can just return LHS.RHS. I don't redo the calculation, but it gives us two different ways of working with the dot product. So I can work with it like this, or I can work with it by going A dot B. Different people have different preferred styles of how they like to write this, and it doesn't really cost us anything to have both. So I kind of tend to go for implementing both ones there. And we can run this, and as we would hope, we get to get the same value for both. So just to recap, we can, for our own classes, set up custom operators. We'll set up support for our different operators. There is a very large range of operators that we can overload. All of our mathematical operators, things like our comparison operators, things like our bitwise, ORing, all of those different ones. There's a lot of different ones that we can override. I've only shown a very, very small segment of it. There are some operators that we can't overload. So things like the scope operator that we see ourselves using here. That is one that you can't overload. But a lot of operators can actually be overloaded. But when we're doing that, there is general sort of syntax that needs to be followed for these. Usually ones where they are something equals. So like an operation equals, so like plus, minus, times, divide. Those ones are usually going to return a reference, whereas the other ones are just going to return typically by value. Most of the ones, the inputs will be a const reference, but if it's something where it's a very simple small type, you might see it be passed by value instead. Sometimes for the operators, we have to actually define them outside of the class. So we'll typically see that needing to set it up outside of the class for things like of our stream insertion operators, for stuff like of our comparison operators. And that can run into difficulties if they're needing to access private data. But we can actually make those operators friends of our class. So if that data is private or protected, we're still able to then access it. So that is something to consider with these, where they can be needing to be set up outside. And you'll find typically examples for all of these. And I will put a link in the description to a reference of, okay, here's all of the different operators that you can typically overload and some examples of how you actually overload those. There are, as I said, a lot more than we have done here, but there is, they all follow a fairly similar pattern. The other thing sort of ran through here is this idea of, okay, just because we can overload all of these operators doesn't necessarily mean we should. And if you're overloading an operator, it should be something where it makes logical sense. And this is a particular thing where, if an operator is assumed to perform a particular function in most scenarios, in particular most scenarios in the base language, going and having it do something very different in your custom implementation is not great. So something like a single pipe, we could make that do a dot product, but that's not how we're used to expecting it to work. Same as I've seen things like using the caret for doing cross product. Again, you could do that, but it's not particularly intuitive, and I don't recommend doing that. What I recommend is setting those up as functions so that if someone goes to try and do those operators, they're not going to work, which is good. And it means then they have a function that is named based upon what the actual operation is it's doing to find. So it makes your code easier to work with, and it means that you're not relying on sort of people having to look up and find, oh, okay, this library uses the pipe operator for doing this, and this one uses multiply and different things like that. So I very strongly would recommend using functions like operator overloading, super powerful, super handy, big fan of it. But let's not go overboard with using it because you can easily turn something into an unreadable mess, which we want to avoid. So dive on in and experiment with this. As I said, I've set up some operators here. There are going to be other ones that you might want to set up, so experiment with setting up those. You could add in things like cross product. You could add in things like getting the magnitude, doing different operations like of that. So those are ones where I would consider as a bit of an experimentation to this, adding in those and see what you can do. Don't stress about breaking any of the code. You've got copies you can grab of it on GitHub, so it doesn't matter if it breaks, and it's your code is always going to break at some point or another. It always happens. So better to view your code breaking as an opportunity to learn how to fix it rather than as you're doing something wrong. It is very much an opportunity, and breaking code is part of learning. Making errors, making bugs, making mistakes is an essential and important part of learning. So if you're creating errors, good news is you're actually engaging in learning there, and that's an important thing to keep in mind with it. Thanks, folks. Hope you found the video interesting and helpful. If you have, try to like and subscribe. It really helps out. It's really appreciated. If you're looking for the code for the project, the code is available up on GitHub, and there is a link to that in the description below. If you've got any questions or other things you'd like to see me do tutorials on, chuck those in a comment below. And if you're looking for other ways to support the channel, then I do have a Patreon, and there's a link to that in the description as well. But until next time,